All right, so today we're going to talk about section 7.4. 7.4 is vectors. Okay, vectors. 7.4, and we're on page 726. So again, you should definitely be reading your text. Make sure you read. I try to cover most of the important things, but there'll always be some things that I don't get to because I simply don't have time to cover any little bitty tidbit. So make sure you're reading. So a vector quantities have both magnitude and direction. So vectors have magnitude and direction. So magnitude and direction, okay? Scalars have magnitude only. Okay? So a vector quantity will have both magnitude and direction, whereas a scalar quantity will have magnitude only. So when you think about scalars, you should be thinking about numbers, okay? I weigh 222 pounds. That's a scalar quantity, right? Or I have $50 in my pocket. That's a scalar quantity. Whereas a vector, again, has both magnitude and direction. So you might think of a vector as a vector, a velocity vector, for example. I can be going 100 miles an hour due north. I gave you both a direction and I gave you a magnitude, a speed. So, and it turns out, and we're going to see this over and over again, so just a little note. Speed is the magnitude of the velocity vector. So I said that velocity is a vector. Again, you have magnitude and direction. Well, speed is an example of a scalar, because speed is the magnitude of the velocity vector. Okay? Speed represents the magnitude of the velocity vector. I might be driving a car 65 miles an hour. That's my speed. I didn't say anything about direction. I said the magnitude of that thing. So that's the difference between scalar quantities and vector quantities. A vector quantity will have both magnitude and direction. A scalar quantity will have magnitude only. Well, when you think about a vector will have an initial point, and it'll point in some direction, okay? It will have some direction. And maybe it goes from one point P to some point Q. Then you can say the vector PQ. Sometimes you'll see this notation. Whenever you see that little bar above, that means it's a vector, okay? And I can measure these things. When you see this notation, PQ, in these double bars, this is the magnitude of PQ. In other words, the length of the vector, the magnitude of PQ. So when you see those double bars, what you're saying is you're going to measure that vector and get the magnitude, all right? So a vector will have an initial point. It might have a terminal point. It may not, okay? But it will definitely have a magnitude, okay? It will have a magnitude. All right. And it will have a direction. A vector has to point in a given specified direction. Now, when we do these things in the book, they use bold, but I'm just going to use that to mean a vector. You see me put that little bar above a letter, that's the vector V, or the vector W, or the vector U, whatever, okay? The book uses bold print, but we're going to use that little bar above the letter, all right? So two vectors are equal if they have the same magnitude and the same direction. This is a fact that you need to know. Two vectors are equal if they have the same magnitude and they point in the same direction. They have to both have the same magnitude and they have to point in the same direction. So with that in mind, example one says vector V goes from, they say 0, 0 to negative 4, 2. Okay, 0, 0 to negative 4, 2. They also say vector W goes from, they give me 2 points for vector W. They say 1, 3 to negative 3, 5. Okay? They say find the magnitudes of vectors. Find the magnitude of both vectors. Okay? So in other words, I want the magnitude of vector V, and I want the magnitude of vector W. This is what we want to find. Okay? Find the magnitude of vector V and the magnitude of vector W. Now, so the first thing I got to do is, magnitude is nothing more than the length, all right, the length of the vector. So if I want a length of a vector that goes from 0, 0 to negative 4, 2, really I can just apply my distance formula, okay? So the distance from that point to this point, again, this is x1, y1, you could call this x2, y2. The distance formula says square root of x2 minus x1, so x2 minus x1, negative 4 minus 0 squared, plus y2 minus y1, 2 minus 0 squared. That's negative 4 squared, or 16. That's 2 squared, or 4. That's square root of 20. 20 is 4 times 5, so square root of 4 is a 2, square root of 5. So the length of vector V is 2 square root of 5. So we just found out that the magnitude of vector V is 2 square root of 5. Because again, the distance from that point to that point represents the length of that vector V. So for W, same thing, apply the distance formula for W. So now these are, W goes from 1, 3 to negative 3, 5. So this is x1, y1. This would be point number 2, x2, y2. Again, just applying the distance formula from Math 171. Distance would be the square root of x2 minus x1, negative 3 minus 1 squared, y2 minus y1 squared, so 5 minus 3 squared. That's negative 4 squared. Negative 4 squared is 16. This is 5 minus 3, or 2 squared. 2 squared is 4. I still get the square root of 20, which is still 2 square root of 5. So we just found out that the length of W is 2 square root of 5. So for V, the length of V was 2 square root of 5. For W, the length of W was 2 square root of 5. So they have the same magnitude. Same magnitude. Okay. Those two vectors have the same magnitude. Now the question becomes, do they have the same direction? Because again, two vectors are equal if they have the same magnitude and the same direction. Well, for direction, again, vector V goes from 0, 0 to negative 4, 2. Vector W goes from 1, 3 to negative 3, 5. If I want to know the direction of the vectors, then basically I can find the slope of that line segment, okay? So let's find the slope of V. All I need to do is apply the slope formula, because my line segment goes from 0, 0 to negative 4, 2. So my slope formula, if you recall, y2 minus y1 over x2 minus x1. So y2 minus y1 would be 2 minus 0 over x2 minus x1, negative 4 minus 0, 2 over negative 4, negative 1/2. Then I calculate the slope of W. Same formula. M equals y2 minus y1, 5 minus 3, x2 minus x1, 5 minus 3 is 2, right? Negative 3 minus 1 is negative 4, that's negative 1/2. So they have the same slope and they have the same magnitude. Yes, V and W are equivalent. So those are, in effect, the same vectors. They're equivalent to each other because they point in the same direction and they have the same magnitude. So those would be equal vectors or equivalent vectors. All right. Next thing we want to talk about is vector addition and vector subtraction. And we're going to do it graphically first. Okay, we're going to do it graphically first. So this is on page 727. So we're going to do it graphically first, then we're going to do it analytically. So vector addition and subtraction. Okay. So again, imagine some vector V. Okay. And imagine some vector W. Okay. Okay. Well, this vector right here, let me put the V in below. When I do this, and if there's vector V, there's vector W, then this would be V plus W. Okay? Now, we're going to learn in a minute that we can think about these two things as technically if these things lived in the XY plane. The XY plane. So vector V was here. Vector W was here. Okay? Again, V plus W, I can think about this vector like this. I can think about taking vector V and then transposing, so I go from the initial point of V to the terminal point of V, right? And then even though W started from here and went up, I can transpose this vector to here and think about it sitting here, okay? Initial point of W here, and I keep the exact same length, same direction as W, and that's how I get this vector V plus W. So this picture applies for this because I can think about W as being transposed so that the initial point of W is at the terminal point of vector V, and then I can imagine W being over here, and hence there's that resultant vector V plus W. Because both vectors might sit in the plane, and really, we just talked about equivalent vectors. Equivalent vectors have the same direction and the same length. So it doesn't matter whether W sits over here and has this length, or it sits over here and has this length. This vector is equivalent to that vector, okay? So that's why I can think of it like this. I can think of V first, and then when I stop at the terminal point of V, place the initial point of W there and point a vector in the same direction of W with the same length, so that W is sitting here, and then that resultant vector here would be V plus W. So that's how I do vector addition graphically, okay? That's how I do vector addition graphically, okay? And if I have a vector, so suppose I have a vector V. Well, let's think about a vector 2V. That would be a vector in the same direction as V, but having twice the length. I could think about 1/2 V. That would be a vector in the same direction of V with 1/2 the length. So anytime I take a vector and I multiply it by a scalar, all I'm doing is changing the length by that factor. I'm not changing the direction, okay? I'm just gonna change the length by that factor. If I have V, if this is 2V, it's just twice as long, pointing in the same direction. If it's 1/2 V, it's half as long, pointing in the same direction. And I could have things like negative V. Negative V would be the vector the same length, but pointing in the opposite direction. Because again, a vector has both direction and magnitude, okay? I could have negative 1/2 V. That's a vector. That would be 1/2 the length of V, pointing in the opposite direction. So this is how I want to think about vectors, okay? There's also a concept called the zero vector. And we're going to do subtraction in a minute, but I'm just going to get this on out the way. The 0 vector. Okay? So a 0 vector has 0 magnitude and has no direction. So the 0 vector has 0 magnitude and no direction. It's just a concept more than anything else. It's just like 0 is for the real numbers or the whole numbers. Okay? There's a concept of a 0 for the vectors. All right? So now let's go back to this addition and subtraction. We saw how to do addition graphically. So let's suppose we wanted to do subtraction. So again, let's suppose we have an XY coordinate system. Some vector V, okay? And suppose I have some vector W, okay? Now we learned that we can take V and we want to do, this time we want to do V minus W. We want to do subtraction. So I learned that V plus W, I could have taken W and I would have just came up here and I'd have drawn W up here, and then that would be V plus W. But since I'm doing V minus W, I'm going to still take V, same length as this vector, same direction, and then W would be up here normally, but I've got minus W. So since it's minus W, I'm going to come in the opposite direction. And there would be V minus W. Okay? So again, W would normally be this. There's V, and then I take the initial point of W, place it there. This vector has the same length as that one. That would have been a positive W. But since I said V minus W, W would go in the opposite direction. The initial point of W would be here, but it would go in the opposite direction, same length. And then this is the resultant vector V minus W. That's how I do subtraction graphically, okay? That's how I'll do subtraction. You can look at this stuff on page 727, 728. All right, well, next thing we're gonna do is we're gonna represent vectors in component form. Represent vectors in component form. We're going to represent vectors in component form, okay? Well, if I think about a vector going from one point, x1, y1, to some second point, x2, y2, okay? And suppose this is P and that's Q. Then I can think about vector PQ. I can actually write an equation for that vector, okay? Because this vector goes, the change in x coordinates is just the x2 minus x1, right? The change in x coordinates. I went from this value of x to this value of x. So the change in x coordinates is from here to here. Change in y coordinates is from here to here. So this would be y2 minus y1. This one would be x2 minus x1. So I can think of vector PQ as x2 minus x1, y2 minus y1. And you'll see this notation. This means vector notation. When you see these two things right here, that means we have a vector, okay? And the other way to think about that is you'll also see this a plus bi, notation. Where does that come from? Well, we already said that I can think about this vector maybe sitting here. I can transpose this P so that it lines up with the origin as long as it has the same direction. That does not look like the same direction. Okay, so suppose that is exactly the same direction as that one. Same length, the length here is the same. Again, it does not matter where that vector sits in the plane. The only thing that matters is they point in the same direction, they have the same length. That's when vectors are equal. When they point in the same direction and they have the same length. So suppose I have this thing at some point AB. There's B, there's A, okay? Well, I can also write this vector, again, I could say AB like that, okay? But since this is in rectangular coordinates, I can also think of this thing, if you think about a unit vector in this direction, okay? Unit vector simply means length 1. So let me just write those two things out. I is going to be a unit vector. Unit vector just means length 1. Length 1. In positive x direction. That's what I is going to represent. J is going to represent a vector, a unit vector, and again length 1 in positive y direction. So what I'm saying is, if I imagine I and J, I is a unit vector in the positive x direction, J is a unit vector in the positive y direction. I can also write a vector as AI plus BJ. So we're going to be able to represent vectors like this, or we're going to be able to represent vectors like that. Either way is fine. Okay? All right. I'm going to leave example 2 to you. That's pretty straightforward. We already said that vectors are equal. Well, let's write that down. This is important. Two vectors are, let's say V equals A1, B1. And W equals A2, B2. Two vectors, V equal A1, B1, and W equals A2, B2, are equal if they say, if and only if A1 equals B1 and, no, A1 equals A2, I'm sorry, and B1 equals B2. That's when two vectors are equal. Okay, V equals W. Vector V equals vector W, if and only if A1 equals A2 and B1 equals B2. Okay. Now, with that in mind, we can add, subtract vectors. Okay. So operations on vectors. If we have two vectors, V, A1, B1, W, A2, B2, then we have vector addition. V plus W. That would simply be A1 plus A2, B1 plus B2. So if I got these two vectors, to add them, I just simply add corresponding coordinates. A1 plus A2 would be the new first coordinate. B1 plus B2 would be the new second coordinate. If I wanted to do subtraction, it's just as straightforward. V minus W. This time I'm going to subtract corresponding coordinates. A1 minus A2, B1 minus B2. Just exactly what you would think. Multiplication by a scalar. Multiplication by a scalar. They say C times a vector, some scalar. Scalar times a vector. Again, a vector will always have that little bar above it. C times a vector would be C, A1, C, B1. Okay? Straightforward stuff. With that in mind, example 3, I will do that one. Example 3. Example 3 on page 730. They say V equals 1, 4. Vector V is 1, 4. And vector W is 3, -2. Okay? So they say A, find V plus W. So I just add corresponding first coordinates. 1 plus 3 makes 4. 4 plus a negative 2 makes 2. So that's V plus W. V minus W is part B. V minus W. Well, that just says 1 minus 3. And then 4 minus a negative 2. 1 minus 3 is negative 2. 4 minus a negative makes 4 plus 2, or 6. Okay? And they show you the that resultant vector. Okay? We'll do that one for part A, and I'll leave part B to you. So X, Y. So vector V was 1, 4. So 1, 4, 1, 4. There's vector V. Vector W is 3, negative 2. 3, negative 2. There's vector W. Okay? Well, again, we talked about subtraction already. If you do V and then come to the terminal side of V, then do, let's do V plus W first. So V plus W, I come to the terminal point of V, then I do W. Again, same length, pointing in the same direction. Then this would be V plus W. And let's see, negative 2, 6. No, V plus W is 4, 2. So 4, 2. So again, I'm doing this by hand, but this should be 4, 2. Okay? And then let's do the negative one, the subtraction. X, Y. 1, 2, 3, 4. So, vector V was still 1, 4. There's V. Vector W is still 3, negative 2. 3, negative 2. So this time let's do subtraction. Okay? This time let's do subtraction. Okay? So we're going to do V first. Okay? And then we're going to do, they did V plus W, and then V minus W. Well, let's see. That's V plus W. That worked out fine. Why is V minus W? Okay. Okay. Let's see what we're doing. So let's do V minus W, okay? V minus W. So I do V, okay? But then instead of doing W, right, I can do negative W, okay? V minus W. And then that would be my vector, okay? That would be my vector. So negative 2, 6. So that's why the vector goes from here to there. Negative 2 up to 6. So that should be V minus W. The point negative 2, 6 would be somewhere up, that should be about negative 6. I'm doing this by hand, but negative 2, 6 should be somewhere up there. That's V minus W. All right, so that's how that works. They've got example 4, it's the same stuff, so I'm gonna let you do that. Properties of vectors is what I'm gonna do next. Properties of vectors, okay? Now they transpose, when you look at the one in the book for this, they transpose that vector over to here, which is fine, okay? Which is fine. That vector essentially has the same length as that vector, okay? That doesn't hurt a thing. Again, it does not matter where a vector sits at in the plane. All that matters, two vectors are equivalent when they have the same magnitude and the same direction. It is irrelevant where they sit at in the plane, okay? That's why it doesn't matter whether I put it here or over there. So the book put it over there, but that's just fine. All right. So properties of vectors. Properties of vectors. So they say U, V, and W are vectors. If U, V, and W are vectors, okay? And they say C and D are scalars. C and D are scalars, so just numbers. Then, so number one, they say V plus W is W plus V. So vector addition is commutative. The order does not matter. Okay. Number two, vector addition is associative. V plus W plus U is the same thing as V plus W plus U. I can change the association. I didn't change the order. The V first, the W second, the U third. But I changed the association. It's the same. Number three, there's a additive identity. A vector V plus the zero vector. Now that's the zero vector. That is not the same thing as zero. This is a vector, okay? That's equal to vector V. That's that additive identity, just like you have in the real numbers. Number four, the additive identity, okay? Number four says that V plus negative V, vector V, plus the opposite vector, well, that is the zero vector. Now again, this equals a vector zero, not a scalar zero, okay? Number five, they say that C times V plus W, a scalar, times vector V plus vector W. That's the same thing as CV plus CW. Okay. Number six, C plus DV. If I add two scalars, multiplied by a vector, that's the same thing as CV plus DV. Number seven, CD times V is the same thing as C times DV. C and D are scalars. Number eight, 1 times a vector is the vector itself. Okay, multiplicative identity. Number 9, the zero. Now this is not a vector, this is just 0. I don't have the bar. 0 times a vector is 0. Well, the zero vector, I'm sorry, the zero vector, yeah. 0, the scalar, times a vector V is equal to 0, the vector. Number 10, C times the zero vector is equal to the zero vector. Those are my properties. And number 11, finally, they say that the length of C times V is equal to IC length of V. Okay? Those are my properties. Okay? Those are the properties. And a lot of these are properties of the real number system, so a lot of those should look pretty familiar to you. A lot of those should look familiar to you. Okay, well, the next thing we want to talk about is finding a unit vector in the direction of a given vector. Find a unit vector in the direction of a given vector. Find a unit vector in the direction of a given vector. So they have a nice formula for that. So here's how we do it. If they say vector V equals AB, so I have some vector AB, okay? Then a unit vector U And again, all unit vector means is a vector of length 1. Unit vectors are vectors of length 1. Then a unit vector, and they say vector u, use the unit vector, and this just means in the direction of v. So the unit vector u in the direction of v, okay, is given by so they say u v 1 over the norm of v times v. That's how I find a unit vector in the direction of a given vector. And since v is a b, I could write this as 1 over the norm of v, a b, and I can push this through and it becomes a over the norm of v, b over the norm of v. So I can write that formula in either one of those 3 versions. So again, this is how I write a vector, a unit vector, length 1, in the direction of a given vector, okay? With that in mind, example 5. Example 5 says, find the unit vector in the direction of vector w, which equals, they say negative 3, 2. I want to find a unit vector in the direction of vector w. Vector w is equal to negative 3, 2. Well, I need to know the length of vector w. Well, that's never anything more than I take the square root of each coordinate squared. Negative 3 squared is 9. 2 squared is 4. Square root of 13. Okay, square root of 13. All right. So my unit vector in the direction of w will be 1 over the square root of 13 times w. W is negative 3, 2. So that would just be negative 3 square root of 13, 2 square root of 13. Okay. If you wanted to, you could rationalize this. Remember how we rationalize? We'll multiply both of these things by the square root of 13 over itself. That's how we rationalize. Do the same thing with 2 over square root of 13. Okay? And your final answer. Final answer for a unit vector in the direction of w is negative 3 square root of 13 over 13, comma, 2 square root of 13 over 13. There would be a unit vector in the direction of vector w. So finding a unit vector in the direction of a given vector is pretty straightforward. Okay? Pretty straightforward. You just got to apply that formula. All right. Nothing hard about that. We talked about representing vectors in IJ form. Okay? So again, vector B, it's AB, I can represent it like that. Well, I can also write it as AI plus BJ, okay? Where again, I is a unit vector in the positive X direction, J is a unit vector in the positive Y direction, okay? So example 6, they say write, they say negative 3, 5. They say, in terms of I and J. Oh, that's easy. So negative 3, 5 equals negative 3i, 5j. And again, I and j are vectors. Keep that in mind. I and j are vectors. They say B says, given w equals 6.2i, vector w, 6.2i, and they say minus 3.4j. So vector w is already in component form, and vector v they give us is negative 1.7i. And then they say plus 2.2j. So I've got these two vectors. They say write 3w minus 5v. 3w minus 5v. Okay? 3w minus 5v. So all I got to do is multiply w by 3. Remember when you multiply by a scale, you just multiply each component by the scale. So I'll have 3 times 6.2i minus 3.4j, and then minus 5 times v, negative 1.7i plus 2.2j. Okay. 3 times 6.2, 18.6i. 3 times 3.49, negative 10.2. Negative 5 times negative 1 makes a positive. 5 times 1.7 is 5, 3.5, 8.5. And then negative 5 times 2.2 makes a negative. Negative 5 times 2.2, negative 5 times 2 is 10. So that's minus 11. So I just distributed those t's. Now I'm going to add components. 18.6 plus 8.5 gives me, and that was negative 10.2. Make sure I did everything right. 18.6, 3 times 3.4. That's 9, 10.2. Yeah, so 18.6 minus 10.2 plus 8.5 minus 11j. All right, we're doing everything right. So now we add the likewise components. So the I components combined, because they're the same component. 18.6 plus 8.5 becomes 27.1i. Negative 10.2j minus 11j becomes negative. 10 minus 11 is negative 21.2. So that would be 3w minus 5v in component form. Nothing hard about that. Okay. All right. They say relate the next objective, objective 5 on page 732. They ask us to relate the component form and direction and magnitude of a vector. Relate the component form and the magnitude and direction of a vector. Okay? We want to relate those two concepts. All right? Well, they do that on page 733 is where they really talk about it. If I've got a vector sitting in the plane, y, x. So I've got some vector. Well, I can think about it as theta is a angle in standard position, right? Theta is some angle in standard position, okay? And if I think about it, this is just my positive x-axis. This distance from here to here would be the normal v cosine of theta. This distance from here to here, this vector ends right here. So this vertical distance would be the normal v sine theta, okay? This distance is that, this distance is that, okay? So if I wanted to, I could write vector v as the norm of v cosine of theta, I, plus the norm of v sine theta, j. So we've related my component and my component form with my form that talks about both magnitude and direction. Because again, the norm of v, that's magnitude, theta is the direction of the vector. So I've related my component form with this idea of, because if I want to think about this as x equals a, y equals b, I could have written this vector as ab. So there's my component form. But again, a is the same thing as the norm of v cosine of theta. B, that length is the same as the norm of b sine of theta. So b equals that, a equals that. So that's what they're talking about by relating those two things. Okay? All right. So with that in mind, example 7. Example 7 says a force of 100 pounds is applied to a hook. Force of 100 pounds is applied to a hook. Okay? On the ceiling at an angle of 45 with the horizontal. With the horizontal. We're going to draw a picture in a moment. Okay? Write the force F in terms of I and J. Write the force F, that's going to be a vector, in terms of I and J. Okay? So, we've got a ceiling, we've got a hook, okay? So, and we got to think about this as being the horizontal, okay? And this is parallel to it, so I've got a weight at some angle theta, okay? And I'm applying this force F, okay? I've got some hanging on this hook and I'm applying a force F at an angle of 45 degrees with the horizontal, okay? And I want to write that force in terms of I and J. Well, they told me a force of 100 pounds, so what they told me was that the norm of F is 100. They gave me the magnitude of the force. It was 100 pounds, okay? So I'm just going to apply that thing. So F is norm of, I'll write it out first. Norm of F cosine theta I plus norm of F sine theta J. But norm of F is 100. Theta is 45, so cosine of 45 I plus 100. Norm of F is 100. Sine of 45 J. Well, I know what cosine of 45 is. It's the square root of 2 over 2 from my unit circle. Same thing here. The sine of 45 is the square root of 2 over 2 from my unit circle. So 2 goes into 150. So I get 50 square root of 2 I plus 50 square root of 2 J. There's my force in terms of I and J. Okay? So I can write this force in terms of its I and J components using that formula that I just erased. Okay? I can write this equation in terms of I and J using that formula. Okay? Example 8 I'll let you do. I'll do example 9. Example 9. These are vectors, so this is objective 6. Vectors and applications. So that just means word problems. Whenever you see the word applications, we're talking about word problems, all right? And, okay. So example 10. Example 10 says, a ship in an open ocean travels 18 miles an hour. A ship in an open ocean travels 18 miles per hour. Okay? At a bearing of north 64 degrees west. At a bearing of north 64 degrees west. Okay? And encounters a current of 4 miles per hour. And encounters a current of 4 miles per hour. Okay? Acting in the direction of north 45 degrees east. Acting in the direction north 45 degrees east. So again, this problem is on page 734. Page 734. This is example 9, I'm sorry, not 10. Example 9, sorry about that. Okay? Round to 1 decimal place. They always usually tell us how to round. Okay, round to 1 decimal place. So A, they want us to express velocity of the ship V. Express velocity of ship. V is going to represent my velocity vector, okay? Relative to the water in terms of I and J. Relative to water in terms of I and J. Okay? All right. Well, I want to express the velocity of the ship V relative to the water in terms of I and J.